Hey guys, I wanted to do a little AP Physics 1 free response question review from last year to help you guys get ready for any upcoming tests, or if anyone's watching this in the future, they just want a quick review. I want this resource to be here. So let's jump into it. Question 1. A cart on a horizontal surface is attached to a spring. The other end of the spring is attached to a wall. The cart is initially held at rest as shown in figure 1. When the cart is released, the system consisting of the cart and string or spring oscillates between positions x equal plus L and x equals minus L. Figure 2 shows the kinetic energy of the cart spring system as a function of the system's potential energy. Frictional forces are negligible. Part A. On the graph of kinetic energy versus potential energy shown in figure 2, the values for the x-intercept and y-intercept are the same. Briefly explain why this is true using physics principles. Okay. So basically we have a cart attached to a little spring here, figure 1. It's oscillating like they said. And we're given a little graph here that's basically showing that the most important part of this question, anything that's going to look like this, is conservation of energy, right? So the idea is kinetic energy goes up, potential energy goes down, potential energy goes up, kinetic energy goes down. Like I said, there's almost definitely going to be a question like this on any future exam, or it's going to at least include this concept. So if you see no energy being taken out of a system, conservation of energy, energy is preserved. All right, let's go to the next one. When the cart is at plus L and momentarily at rest, a block is dropped onto the cart, as shown in figure 3. The block sticks to the cart, and the block cart spring system continues to oscillate between negative L and plus L. The masses of the cart and the block are m and 3m, respectively. The frequency of oscillation before the block is dropped onto the cart is F1. The frequency of oscillation after the block is dropped onto the cart is F2. Calculate the numerical value of the ratio F2 over F1. Okay, so going into a question like this, you see they give us some masses and they want us to find a ratio. I think it's pretty safe to assume that we're going to be using formulas and building our ratio here. I got my sheet up here, and I think the formulas we're going to be using here: T equals 1 over F, and T equals 2 pi m over K. Now we're going to combine these and build our frequencies, and then, put them into a ratio. So let's start. We'll do it in steps. We'll do 1 over F1 is going to equal 2 pi m over K. 1 over F2 equals 2 pi 4m over K. And it's 4 because we have 3 and 1 combined. So use 1 and use 4. Now we can flip them just to make it a little bit easier to understand. 1 over 2 pi. These flip. 1 over 2 pi. These flip. Okay, now it's F2 over F1. We can also do a little simplify here. Pull the 4 out. This is going to be 4 pi m. Okay, now we're going F2 over F1. So we have 1 over 4 pi kmo. Then we're going to have 1 over 2 pi kmo. We can simplify here. We get rid of this, right? So F2 over F1. I'm seeing 1 over 2, or 1 over 1. This is a 1. We're going to need to flip them, just to make it easier to understand. So it's going to be 1 over 2. as our final ratio. Like I said, the most important parts for this question are when you see things that look like they want to be plugged into equations and you find a ratio. It's pretty safe to think about your equation sheet and try to find an actual numerical answer. Okay, question 3, or part C. The dashed line in figure 4 shows the kinetic energy K versus potential energy U of the block cart spring system after the block is dropped onto the cart. This graph is identical to the graph shown in figure 2 for the cart spring system before the block is dropped onto the cart. Briefly explain why the two graphs must be the same using physics principles. Okay, and like we said before, the big idea here is still conservation of energy, right? So, there's no work being done. Our graph's going to stay the exact same. Conservation of energy. Like I said, it's an important concept. It'll definitely come up on future tests. If you see no energy being taken out, then good to result back to it. Next part, after the block is dropped onto the cart, consider a system that consists only of the cart and the spring. On figure 4, sketch a solid line that shows the kinetic energy of the system that consists of the cart and the spring, but not the block after the block is dropped onto the cart. Okay. Now, like I said before, conservation of energy, important concept, and here we're going to be considering the total energy. And since we knew from before our two blocks, our new block was 3 times the mass of the original, our kinetic energy is going to be dropping by that much, that ratio. So right here we're at 4, we're going to be dropping down to 1, but our potential energy is going to stay the same. So our new line is going to look like that. Like I said, important parts for this section, conservation of energy. If you see things that look like they're going to be plugged in, and you see a ratio, or you see something that wants a numerical answer, look back at your equation sheet. And let me know what section you guys want me to do next. Happy to help, and see you guys soon.